A massive 1-ton load of sugarcane enters the factory, yet in the end, only about 120 kilograms of it becomes sugar. So where do the remaining nearly 900 kilograms of water, fiber, and impurities go? To recover that limited amount of sucrose, sugarcane must first grow for months under the sun. It is then swept from the fields by enormous harvesting machines and rushed to the factory before its sugar content begins to decline. Inside, the tough stalks are chopped apart and crushed through a series of heavy rollers. The cloudy cane juice is then clarified, concentrated into syrup, and forced to crystallize. Finally, high-speed centrifuges strip the molasses away from the crystals, while streams of hot air dry them into clean, bright sugar grains ready for packaging. Join Factron Process as we step inside the production line and discover how a stalk of sugarcane from the field is transformed into the familiar sugar crystals found in your kitchen. Few people realize that the tiny sugar crystals in their kitchens are part of an industry worth around $75 billion a year. To keep this enormous system running, more than 2 billion tons of sugarcane are harvested worldwide, making it one of the most heavily produced crops on the planet. Most of the world's sugar is still made from sugarcane and appears in thousands of products, from candy, soft drinks, and dairy products to pharmaceuticals and processed foods. But the most surprising part is that these factories do more than produce sweetness. The fibrous residue left after crushing can be burned to generate steam and electricity, helping power the production line itself. In this way, a modern sugar mill can also operate as a biomass energy plant. The journey of sugar begins in tropical fields, where sunlight, water, and time quietly transform sugarcane into a natural storehouse of sucrose. First, heavy-duty plows cut deep into the soil, breaking apart compacted layers before shaping the field into long, evenly spaced rows. Sugarcane is not grown from seed. Healthy stalks are cut into sections containing viable buds and loaded into specialized planting machines. In a single pass, the machine opens the furrow, distributes fertilizer, places the cane cuttings into the soil, and covers them again, allowing thousands of planting sections to be positioned quickly and evenly. Once the buds begin to sprout, tractors continue moving along the rows to control weeds, mound soil around the base, apply additional nutrients, and support irrigation. Over the next 10 to 18 months, the plants continuously draw in water, absorb sunlight, and concentrate sugar inside their stalks, eventually reaching heights of about 6.5 to more than 13 feet. But taller stalks do not necessarily contain more sugar. Sucrose is usually most concentrated near the base, where the cane matures earlier than the upper sections. Raising the cutting blade by only a few inches can leave some of the most valuable raw material behind in the field. When the sugar content inside the stalks reaches its peak, lines of fire are lit across the field. Within minutes, dry leaves, weeds, and the outer sheaths are burned away. But the cane itself does not easily catch fire. Its high water content protects the sugar-rich stalks, while the flames remove unwanted plant material and clear the rows for harvesting machines. However, field burning also creates smoke dust and biomass loss. For this reason, many regions are shifting to green cane harvesting, where machines cut the crop without fire and leave the separated leaves and tops on the ground as mulch. Minutes after the flames pass, millions of sugar-filled stalks remain standing, ready for harvest. When the sugar has reached its peak concentration within every section of the stalk, the field arrives at the most anticipated moment of the entire growing season, the harvest. The sugarcane harvester moves into the field like a giant machine, swallowing entire rows of cane. At the front, row dividers guide the leaning stalks into the cutting path. A topper sweeps away the leaves above, while two high-speed steel discs drop close to the ground and slice through the base, the part containing the highest concentration of sugar. But cutting lower is not always better. If the blades are set too high, part of the sucrose-rich stalk is left behind. If they cut too deep, the machine may pull in soil and rocks and damage the cane stubble needed for the next ratoon crop. The moment the stalks leave the ground, feed rollers pull them into the machine and chop them continuously into short sections. A powerful blast of air immediately blows away leaves, dust, and other lightweight material. The heavier cane pieces continue along a conveyor and are discharged directly into a transport vehicle moving alongside the harvester. In a single pass, the machine completes 5 tasks: topping, base cutting, chopping, cleaning, and loading. Under favorable conditions, one harvester can process dozens of tons, sometimes nearly 100 tons, of sugarcane per hour, enough to fill several large trucks before the roar of its engine fades across the field. As soon as the field carrier is full, the sugarcane is transferred into large trucks or dedicated rail cars. Each load can carry roughly 33 to 44 tons of raw material, about the weight of more than 20 passenger cars. But this is more than a simple journey from field to factory. It is a race against time. From the moment the cane is cut, the sucrose inside begins to break down, and every hour of delay can mean less recoverable sugar from the same load. That is why the convoys keep moving almost without pause, carrying the freshly harvested cane straight to the mill before its valuable sweetness begins to fade. The moment the cane hits the conveyor, it enters what looks like an industrial-scale shower. High-pressure water jets sweep across the stalks, blasting away layers of mud, sand, and field dust. Next, vibrating screens separate stones, twigs, and other large debris before they can travel deeper into the production line. In modern mills, the cane may also tumble through swirling wash tanks or rotating drums, where rushing water strips away the remaining impurities like a giant washing machine. Within minutes, dozens of tons of cane emerge clean, protecting the cutting blades and crushing rollers while delivering a purer stream of juice for the stages ahead. Once cleaned, the sugarcane moves into one of the most critical sections of the production line, the point where the first drops of sugar-rich juice are released from the plant's fibrous structure. Thousands of blades continuously chop, tear, and shred the stalks into thin strands. The goal is not to extract the juice immediately, but to rupture the structure of millions of plant cells, creating a path for the sucrose locked inside to escape during the next stage. The loosened mass of cane fiber is then fed through a series of crushing mills, made up of multiple pairs of enormous steel rollers arranged in sequence. Each roller measures more than 3 feet in diameter and rotates against its partner under pressures reaching hundreds of tons. After every pressing, the remaining fiber still holds a significant amount of sugar. To recover it, the system sprays hot water or diluted cane juice across the bagasse before sending it into the next set of rollers. This process, known as imbibition, works much like repeatedly rinsing a towel soaked with syrup. The water penetrates deep into the fibers, dissolves the remaining sucrose, and is pressed out once again, helping the mill push sugar recovery as high as possible. After repeated cycles of shredding, imbibition, and crushing, nearly all recoverable sugar has been separated from the cane. From every ton of sugar cane, the mill can collect roughly 170 to 190 gallons of raw juice. Although the remaining bagasse may look like nothing more than a pile of wet, exhausted fiber, it still holds a remarkable amount of energy. Instead of being discarded as waste, it begins a new journey, becoming one of the main fuels used to power the mill itself. After leaving the crushing mills, the raw cane juice remains a cloudy greenish-brown liquid, carrying fine soil, proteins, plant waxes, and countless particles too small to be seen with the naked eye. As milk of lime is added and the juice is heated, its acidity is gradually brought under control, while the suspended impurities begin to bind together. Here, gravity quietly takes over. The heavy sludge slowly settles to the bottom, while the clearer, cleaner juice is continuously collected from above. Yet even after clarification, most of the juice is still water. How can a mill remove thousands of tons of water every day without scorching the sugar? The answer lies in a multiple effect evaporation system. Vapor from the first evaporator is reused to heat the next, while the pressure drops from stage to stage, allowing water to boil at lower temperatures. This saves energy and helps protect the sucrose from degradation. With each stage, the thin cane juice loses more water and gradually transforms into a thick golden brown syrup. Technicians take samples and measure the Brix level to determine whether the syrup has reached the required concentration. The syrup is then pumped into vacuum pans. Once the solution becomes supersaturated, extremely fine sugar crystals are added as seed crystals. Sucrose molecules continuously attach to their surfaces, causing the crystals to grow. The amount of seed must be controlled precisely. Too much produces sugar as fine as dust, while too little creates oversized, uneven crystals. Finally, the vacuum pan produces masacuite, a dense mixture of sugar crystals and molasses. It may look like thick brown sludge, but hidden inside are millions of crystals waiting to be separated. Once the syrup reaches the required concentration, it is pumped into a vacuum pan, where reduced pressure allows the remaining water to evaporate without exposing the sugar to excessive heat. Tiny seed crystals are then introduced, giving sucrose molecules a surface to attach to as the crystals gradually grow. Throughout the process, temperature, pressure, and agitation are carefully controlled to keep the crystals uniform. The result is masacuite, a thick mixture of sugar crystals and molasses, ready to be transferred to the centrifuges for separation. Inside the centrifuge, the masacuite is loaded into a perforated steel basket, and the entire machine quickly accelerates to between 1,000 and 1,800 revolutions per minute. Within seconds, centrifugal force, hundreds of times stronger than Earth's gravity, presses the sugar crystals tightly against the basket wall, while the liquid molasses is forced through thousands of tiny openings and drained into a recovery system below. Once most of the molasses has been removed, many factories spray a small amount of hot water or steam across the crystal layer. This brief washing step strips away the thin film of molasses still clinging to the surface while minimizing the amount of sugar that dissolves. If the washing lasts too long, part of the finished product can dissolve back into the liquid, reducing the factory's total sugar yield. The separated molasses is far from waste. Although it remains sweet, it contains minerals and organic compounds, making it valuable for producing ethanol, rum, yeast, and animal feed. The remaining sugar crystals can reach a purity of roughly 97 to 99%, but they still carry a small amount of surface moisture. Before they can be packaged, they must move to the drying stage, where they become dry, free-flowing, and stable during storage. After leaving the centrifuge, the sugar crystals still retain about 1 to 2% moisture, a seemingly small amount, but enough to make an entire batch begin clumping if it is not treated quickly. That is why the crystals are immediately transferred into a fluidized bed dryer or a hot air conveyor system. Inside a fluidized bed dryer, air heated to approximately 250 to 300 degrees Fahrenheit is forced upward from below, lifting millions of crystals and making them behave almost like a flowing liquid. Moisture evaporates rapidly, while the shape of each crystal remains intact. In conveyor-based systems, the sugar travels across a perforated belt as a continuous stream of hot, dry air passes through it. The temperature must be controlled with extreme precision. Too much heat can discolor the sugar. Too little drying leaves moisture trapped inside. By the end of the process, the moisture level has fallen to just 0.02 to 0.05%, leaving the crystals dry, free-flowing, and stable for long-term storage. Once fully cooled, the sugar flows from large storage silos into an automated weighing system. In a fraction of a second, sensors calculate the exact amount required for each package. From small household bags weighing only a few pounds to industrial sacks of more than 50 pounds. Along the packaging line, rolls of material are continuously pulled forward, formed into bags, sealed at the bottom, and filled with precisely measured sugar. The opening is then sealed, while the production date, batch code, and traceability information are printed onto the package. Each bag immediately passes across a check weigher. A deviation of only a few grams is enough for the system to reject it automatically. At the end of the line, robots stack the bags in interlocking layers on pallets before wrapping them in protective film. And here's the surprising part. Sugar's greatest enemy is not bacteria, but moisture. A single cooling or storage failure can turn millions of free-flowing crystals into massive solid blocks. Most cane sugar leaving the factory does not go straight into household kitchens. Instead, it is shipped in bulk to confectionery, beverage, dairy, ice cream, processed food, and pharmaceutical plants. By changing only the temperature, heating time, and water content, the same sugar can become soft caramel, thick syrup, clear hard candy, or a crisp coating for desserts. In beverage factories, it is dissolved into concentrated syrup and precisely measured into every production batch to maintain a consistent flavor. Some of the crystals are ground into an ultrafine powder for frostings, fillings, and fast-dissolving products. In pharmaceuticals, sucrose is also used in medicinal syrups, tablets, and protective coatings. From everyday foods to massive processing lines, cane sugar has become a fundamental ingredient of modern industry. And with that, we have followed the entire journey of cane sugar, from planting and caring for vast sugarcane fields, to harvesting, transportation, crushing, juice extraction, evaporation, crystallization, drying, and finally packaging the finished product. Behind that familiar sweetness lies a massive production chain, where agriculture, mechanical engineering, thermal energy, and processing technology work continuously together to transform rough sugarcane stalks into billions of white sugar crystals. And the process creates far more than sugar. Bagasse and molasses are also recovered and used to produce electricity, ethanol, animal feed, and a wide range of bio-based materials. If you found this journey fascinating, don't forget to like, subscribe, and turn on notifications to join Factron Process for more remarkable stories from the world of industry.